Well, good evening, ladies and gentlemen, and thanks for this great turnout on such horrible weather night. I was up at Curry today and there was plenty of snow up there, so there must be quite a lot around Edinburgh. Anyway, welcome to 2025, and Happy New Year. Our 100 years is now finished, I suppose, actually, but it was last year. But we're still celebrating anyway, because to make it to 100 years is good for anybody. I think. So we'll carry on. So, for this evening, a number of things on the agenda. We're going to do the Image of the Year 2024 results. So that's very interesting. It's been a great year for imaging. What's happening soon? And then we've got Colin Snodgrass doing what we've seen from the DART mission, which is really looking forward to that. And then Nigel's going to tell us about the sky in January, and hopefully it's going to stay clear as it has been in the last couple of nights. And if I could remind those on Zoom, please to mute. Sometimes we hear dogs, babies, and televisions in the background. Fantastic shot by Ian of the Earth's rotation. So the Image of the Year competition, we have an Image of the Quarter competition, which runs through the year. This year we called for an Image of the Year. We had 17 entries. The votes were cast by the members as to who should win. And the winner won by 1 vote, so it was very close. There was a lot of really good images. As you can see, last year's winner, David Harvey with the Horsehead Nebula, and all sorts of other things going on. So, without further ado. So in third place is David Brett. Is David here tonight? No. Quite an interesting lineup of all the planets. I'm not sure they're all to scale, but you can actually see them all. And excellent crispness in that. Joint second place. Eros was one of his amazing time lapses, and I'm going to play this. So. Absolutely amazing video, which you can see the whole of and on the website. Joint second place, Ian Smith, was an amazing photograph of the Needle Galaxy, NGC 4565. Amazing detail there. I don't know if you can see it on the screens, but there's incredible detail in the dust lanes, and that side-on view is spectacular. And just a quick question for Alan, what's the galaxy down below left? And first place, again Eros, the Elephant's Trunk Nebula, IC 1396. He wins the prize. And also, I suppose this view is a more traditional view of it, but as we know, there's no way up or down in space. So, so if Eros is out there, hopefully listening. Is he Eros on the call? No, well, congratulations, Eros. Well done. So these are meetings we've got coming soon. Real images of exoplanets. That's a bit of a challenge for most of us, but we do get some information from exoplanets these days. We're running a project on that subject. And then the European Extremely Large Telescope, looking forward to that, and basically setting up how they actually analyze all the stuff they get. Now, our normal imaging observing group, which is online and for members only, although we invite more and more members to come along to that, because it's a great learning experience. On 21st of February, John Mowat and the first Chilean observatory. I have to say, I don't know anything about John Mowat, so I'm looking forward to that. Now, there's a members' night on the 4th of April. On our members' nights, that tends to be, we like to get members to do short presentations or a talk or whatever they want, bring something along to show everybody. So please let Mark know, it's the best way, let Mark know what you would like to talk about or bring along. So it's now over to Colin and another fascinating talk. Come on. There we go.
Green, that's probably working. Okay, good. So yes, what I'm going to tell you a little bit about is the NASA DART mission and some results from it. But as this is a group of astronomers and as I'm an astronomer, I'm also going to tell you more about the observations that went along with this and the fact that this wasn't just something that we did with a space mission. This is something that we had a large campaign of telescopes studying the effects of this mission as well. So, the DART mission, this is humanity's first attempt to deflect an asteroid, change an asteroid from its trajectory, as a practice in case we ever find one coming for us when we want to do this for real. I will stress, as I keep getting told to stress by my friends on this mission, this was just a practice, this was not going to hit us. But occasionally they do. Occasionally rocks fall from the sky. This one it was one of the handful, there's now about 10 examples where we've discovered an asteroid in space as an asteroid. It's been found by a sky survey and catalogued as an asteroid and its trajectory calculated. And we've looked at that trajectory and gone, oh, that's coming for us. And there's a few now that have been done, but they've all been very small. And in a few cases like this, we've been able to say, oh, in a few hours to maybe a day or so, this thing's going to hit the atmosphere. It's going to hit about here. If you watch out tonight, you'll see a bright fireball. And if you're lucky, you might go and find some meteorites in the morning. And this is one of these ones. This was in 2023. One of these things was discovered a few hours before it was going to hit Earth's atmosphere. And it entered the atmosphere over southern England and northern France, went over the channel. And people who were paying attention to this were watching out. And this is a little video of someone took of this bright fireball over Brighton. And then the picture that you see on the side of that, this is a fragment from it. This is a bit of that meteorite. And this is well, I took the picture, I'm not holding it. This is being held by one of the curators at National History Museum in Vienna a month later, and gone and found this, so this is about as fresh a meteorite as you're going to ever see. This thing was just come in from space. Yeah. So there's a few of these cases now where we're finding these things. And this scale of asteroid hits us all the time. Anytime you see a bright fireball like this, anytime you see a shooting star, this is a small asteroid. A bright fireball like this one is a slightly bigger one. These happen all the time. This is a map which of the sort of larger fireballs that have been picked up by US government sensors. So they've got lots of sensors around, mostly looking out for people doing nuclear tests or other things like this that they want to know about, but they're also quite good at picking up fireballs coming in from space. And you can see they're scattered all over the place, and these are varying different scales. The large red dot over Russia, this was one of the larger ones in recent times. This was a Chelyabinsk fireball that you might have seen pictures of on videos of on the news just over a decade ago now. There were lots of images of this, lots of videos from dash cams particularly of this bright fireball in the sky. And this was something that entered the sky out near to the city of Chelyabinsk in Russia and caused a lot of damage, caused quite a lot of injuries, but luckily nothing too serious. But mostly because lots of people saw this bright light in the sky, went over to their window to go, what was that? And light travels faster than sound, so when you see a bright flash in the sky, move away from the window because the shockwave and the broken glass will come a few seconds later. But yeah, so it caused a lot of damage, but luckily it wasn't directly over the city. Yeah. That was caused by something that was an asteroid about 20 meters in diameter. And that gave a really bright fireball like this and a big explosion in the sky. Things that are meter type scale are big enough to give you a fireball and maybe some meteorites. Something that's on this tens of meters, 20 meter scale is enough to cause some real damage and cause, if it was directly over a city, it would have been a problem. As you get bigger, you get a bigger amount of damage. Yeah? So one of the most famous impacts from an asteroid is Meteor Crater in Arizona, which is quite an impressive thing to see. This thing's about a mile across, and this was caused by something about a 50-meter diameter asteroid. And so this is something you really don't want hitting over your city. This caused, at the time this would have hit, this would have caused, a fireball over 10-kilometer radius, caused huge damage out over many kilometers. There's this nice map that shows, sort of centered on Meteor Crater in Arizona, the damage going out. But if you've ever been to Meteor Crater in Arizona, it's in the middle of nowhere. There is nothing around there. So even if it happened today, it wouldn't really cause that much damage. I can put the same circles, though, however, Edinburgh, to give you an idea of scale. So it would be bad if that landed here. Yeah, this is basically flattens everything out across the borders in Fife and completely wipes out Edinburgh. So tens of meters, 50-meter, 100-meter scale asteroids are a problem. But this is where we get into the scales of asteroids, and the fact is there are many more small ones than there are large ones. Yeah. So the meter-sized things that give us these bright fireballs, they are happening quite regularly. You'll get something of a few meters size hitting the atmosphere once a year and giving you bright fireballs and some meteorites somewhere. When you get up to something that's of the sort of a few tens of meters size, 25 meters size or so, there's going to happen once a century-ish, something like that. The 150 meters, something like this is going to happen on a 10,000-year time scale. If you go all the way up to the sort of 10-kilometer size asteroid, that's the global extinction event. That's the kills your dinosaurs type scale. Those happen on a millions of years time scale, hundreds of millions of years time scale. But on the very largest scale, there's very few of them around. There are 4 of those in asteroids in near-Earth space. And we know where all those 4 are, and they're not coming anywhere near us. So we're not worried about those. At the very bottom end of the scale, there's probably 500 million things that are meter-sized scale. We know where very, very few of them are because we tend to discover them only hours before they hit the atmosphere. But we're also not worried about those because all they're going to do is drop you a nice meteorite, and that's going to be very interesting. Where we're slightly more concerned is somewhere in the middle of this plot. Where things of the 100-meter scale are, we know there's probably 20,000, 30,000, a few tens of thousands of these things out there somewhere. And we know where less than half of them are. And we're working on improving that. But those are the things which, they're not going to wipe out life on Earth, but you wouldn't want them to land on your city. Those are the scale where, concern is probably too strong a word, but, they are the scale where potentially they could cause a lot of destruction, but also potentially we could do something about it. And so therefore, that's where planetary protection efforts are paying attention to them. And so, so we're not too worried about like the big ones. But yeah, the intermediate size things are where we need to think about. And so there is this effort globally, which has this, we like to give ourselves the very grand title of planetary defense, because it makes us feel important. And this covers a whole bunch of different topics. It covers the searching for these things in the first place, telescope surveys, scanning the skies, trying to find new asteroids. It covers sort of follow-up observations. Once you've discovered them, trying to characterize them, discover what they're made of, how big are they, following their orbits and refining the orbits and discovering whether or not they really present a danger or not. And then there's also the side of this which is talking about, well, what would you do if one of these things was actually coming for you? And there's a lot of planning and there's a lot of discussion goes into that. And there's meetings every couple of years where you discuss not just the practicalities of all of this and the science of it, but also the politics. And there's people that come to these things that come from sort of like, the disaster management communities, people that plan for national disasters. What would you do if one thing was coming? So this is actually considered at government levels. People are paying attention. There's a UN body that also kind of oversees a lot of this effort. And then the bit which is where the DART mission comes into is that there's effort being put into what would you do if you found one coming? How could you mitigate this? What could you do to change the course of an asteroid? And this is where the DART mission comes in. The DART was a test of technology to see what could we do if an asteroid was coming for us. And so it's been the top priority for a while in the planetary defense community, because it is the technology that you would use in the kind of range of size of object that, as I said, are common enough that there maybe is one out there with our name on it, and big enough that it would cause enough damage, but small enough that we could do something about it. There's this plot that kind of tries to show the range of different techniques that you might apply for a different size of asteroid for a different amount of warning time. So at the bottom of the plot, if the asteroid's quite small, then what you do about it is you move the people out the way. Civil defense. Yeah, if you spot one coming that's big enough to take out a city but not really do anything more about it, and you've only got a couple of years warning, then you've got enough time to get everyone out of the way. If you've got much longer time scales, you can do something about it. These things that are on this 100-meter scale are the right size for us to try this technique called the kinetic impactor, which is a fancy word for smack a spacecraft into it as hard as you can and give it a nudge. And then if you go up to much larger scales or very short warning times, your only options are nuclear weapons, but no one wants to try testing those. The politics get very interesting. So we have these different areas of the space, but the area where we could do something about it and where there is this potential risk is this area where we could do something on this 100-meter scale and try it with these kinetic impactors. Okay, so the DART mission. The DART mission was exactly this idea, kinetic impactor. Crash your spacecraft into an asteroid as hard as you possibly can, and then change its course by doing this. It's playing billiards with asteroids. It is just kinetic energy and smacking into it. But the DART mission was very clever. DART stands for Double Asteroid Redirect Test. And the reason why this is clever is because it wasn't just going to a single asteroid, it was going to an asteroid binary system. So a larger asteroid called Didymos with a smaller moon, a smaller asteroid in orbit around it called Dimorphos. And the reason why this is a good way to test this is because what we did was we hit the smaller asteroid in this system and we changed its orbit around the primary asteroid rather than trying to change the orbit of an asteroid around the sun. Now, the reason why this is a good way to test this is because the small asteroid is orbiting the larger asteroid about once every 12 hours. And so if you change its orbit by a small amount, you will see the effect the next day, and the next day, and the next day. Whereas if this thing's orbiting the sun and it takes 3 or 4 years to orbit it, and you change it by a small amount, you've got to measure that small change over decades timescale. And so this was a nice way of measuring the change of this. And also it's a nice way of containing your experiment, because the question that everybody always asked when we were doing the build up to this, they were like, have you checked the maths? Are you sure you're not going to nudge the asteroid towards us by accident? And the answer was always yes, but this is one of the other ways of making sure you're not doing that. We weren't changing the orbit of this thing around the sun at all. It's still in the same orbit. It's not coming anywhere near us, but you're changing the small asteroid's orbit around the larger asteroid. So yeah, DART mission launched in November 2021, took just under a year to get there, crashed into there at the end of September 2022. It carried along with it this thing called LithiaCube, which is a little CubeSat with cameras on it to record from up close the effect of the impact, because the main spacecraft is destroyed in the impact, of course. And then, as I said, I'll tell you a little bit about, we were observing this from the ground, because again, your spacecraft's destroyed in the impact, so if you want to measure the effects, you want to do this in a way that you can measure this with telescopes on Earth. And so this is the idea. It crashes into Dimorphos. It then changes that orbit. It moves onto a new orbit around Didymos, and then we measure the effect of that change by remeasuring the orbit of the small asteroid around the larger one. Okay, I said that the scale of the things that we're kind of concerned of is the sort of 100-meter scale. This is a nice little plot of showing you the scale of these asteroids. So Didymos is the big one, is the primary. This is on the scale where it would take quite a lot of effort to shift that, kind of almost kilometer scale, but on the size where they're rarer and they're not coming towards us. Dimorphos is the size of the smaller one. It's kind of, you know, scale of the Great Pyramid. Yeah? Not something you want to fall on you, but something that you could move by giving it a nudge. And then the spacecraft itself is also on this plot that is quite small. So the spacecraft is small compared to the asteroid, but its spacecraft's going very fast. Kinetic energy goes as velocity squared. If you go with a fast enough crash, you put with quite a lot of punch. This is the actual spacecraft in a clean room, Johns Hopkins, before it goes, with person for scale. It has rolled up solar panels on the sides, one of the new technologies that it had on it. It had these solar panels that deploy and unroll, which is quite neat. The spacecraft was a relatively simple one. So all it had was rockets and a camera on the front, and solar powers and for radios and so on, and then a box to release this other little CubeSat from it. It wasn't covered in instrumentation the way you would think of most scientific probes, because it was designed just to be a bullet and crash into something. But essentially it's an instrumented missile that has a camera for guidance, and then onboard computer to allow it to go and hit its target. Because this is the images that comes from that camera. And these were streamed live onto the internet while we were doing this. I don't know if anyone was watching it at the time. It hit about 1 o'clock in the morning, UK time. But they were streaming the data straight out onto the internet. And it meant that in real time you could watch and you could see these asteroids, and you see the larger one going past as we get closer on to the first one. Here I've sped up the images. And then as we get into the last few images, this is now going real time in seconds. And then the last image that we get there, and then the very last image, you only get some of, because at this point your spacecraft is an expanding cloud of debris, and so we don't get the rest of that image back. But we could tell that it worked in real time, and everyone who was watching online could tell that it worked in real time, because all of a sudden it went from an image of, oh, some rocks, to no image. These are some of the images, you know, picked out of that sequence to give you some idea of the images we see. We learn a lot about the asteroids just from this. I mean, it's not an instrumented probe, it's really just a missile. But even from these images from navigation, you learn something about the asteroids. In this image, you can see the larger asteroid has kind of a sort of smoother region around the sort of waist of it, around its equator. This helps us confirm some of the ideas we have of how these binary asteroid systems form. That a small asteroid like this binary one is actually formed because the large one has spun faster and faster until material sort of slides down onto the equator. And then as it keeps spinning, some of that leaves the equator, goes into orbit, forms into a smaller one going around it. And so you learn something about processes and geology and so on just from these images. If we zoom into Dimorphos, so the actual target itself, it really shows that this is one of these, what we call a rubble pile. These are we think that these asteroids they're really held together just by self-gravity. There's not a lot of material strength to them. And that's something that obviously will be important if you were actually trying to deflect one that was coming for you. You want to know about the material properties. What are you trying to hit? If it's a sandbag or if it's a solid block, this is going to make a big difference to deflecting it. It's also going to make a big difference to what happens when it hits you. So this is the last image where you see the whole of of Dimorphos. And then this is the last complete image that we got down. This thing is 2 seconds before the impact. At this point, it's still 7 miles away. It was going quite fast. So this is the sort of big boulders you see in the middle are meters across or 10 meters across scale. They're quite large boulders, and we managed to hit right in between a couple of them there, just by chance. This is the sort of sequence of images as you see it going in, and you get kind of finer and finer resolution on the surface. I said up until that last image where we don't get all of it. That's that last full image, but overlaid on it, that's the outline of the spacecraft with the central body and with the solar panels sticking out, just to give you the scale of it. And we hit between these two boulders that have been given names, Atabaque and Bodran. All of the features on this have got names based on percussion instruments from all around the world. Because we like to use a theme when we name stuff on celestial bodies, and this one, because we thought we're going to smack it quite hard, we'll name everything after drums. And then you can reconstruct a kind of 3D model of the surface and the 3D model of the spacecraft, and this is sort of how it hits, and all of this is going into understanding the physics of the collision. And people are doing modeling on very fine scales of, does it make a difference that you hit between two boulders instead of hitting a boulder or hitting an area that was kind of smaller particles? And there's a lot of kind of studying going on with simulations to understand that stuff. Okay, so DART mission had basically 4 top-level requirements. If you do a mission with NASA, everything is, what's the requirements? What does this have to achieve for us to be able to tick and say, success, landed here, did this. And so the first goal is we have to hit the target, which is non-trivial. I mean, it was very impressive that it zoomed right in and it hit it. And if you were watching as you were doing the approach video, you see it moves around a little bit. That's when the spacecraft's firing the thrusters and correcting, and it's all doing this on software. It's going too fast for anyone to control it on the ground. And so, firstly, it did hit, and it hit the right one, because it had to pick 2 targets and hit the right one. So yeah, that worked. We saw that the spacecraft stopped sending images, so pretty sure it hit. The second thing is it had to actually change the orbit. And if it just hit and nothing happened, then, well, we learned something about planetary defense, but it would still not have achieved the goals we were aiming to do. And so we had to see that it somehow changed the orbit. And then the next step was to see, well, how much did it change the orbit by? Measure this. And this is where the ground-based observations come in, because the spacecraft no longer exists, so you have to do this with a telescope. And then the last thing is measure this factor that we call beta, which is the enhancement factor you get when you crash into a loose pile of rocks like this, from the fact that some of the rocks are also thrown out. This is sort of illustrated with this sketch here, that if you don't have any ejector, your collision is just conservation of momentum and it's just billiards. Yeah? It will move the asteroid by the same amount of momentum you put in. But if you create a hole on the surface, you create a crater, and from that crater some ejector, some material is thrown out. That's thrown out in the opposite direction you hit from it, and it means that the whole thing's behaving like a rocket. Yeah? A rocket works because you throw material out the back and it pushes you forwards. And you can do the same thing with an asteroid. If the asteroid starts throwing out material because you've hit it quite hard and made a crater, then how much of that material it throws out will act to also accelerate the asteroid. So you have this factor that we call beta, which is a sort of multiplier on how effective is moving an asteroid just by colliding with it. Yeah, beta of 1 means all you've done is just hit it by the amount that your spacecraft was going. Beta of more than 1 means that it's more effective than that, and it means you can, if you were doing this for real, if you know that beta is actually 3 or 4, then you can then say, well, actually I can get away with a factor of 3 or 4 less mass of my spacecraft and still achieve the goal I need. Yeah. So that's why that's an important thing to understand from the planetary defense. Okay, so measuring all this, as I said, we did this from the ground. We did this with telescopes. There's a large campaign of people that were observing from this, and we had most major observatories and a few minor ones on the ground. And then we also had things in space like Hubble and JWST. And then also some observations from the Lucy mission, which is a NASA mission on its way out to the Trojan asteroids, which also happened to be swinging past Earth for a gravity assist about the right time, and then they used the cameras on that as a space telescope. But yeah, all of these sort of major professional telescopes all over the world. And what were we doing? Well, we were doing lots of things, spectroscopy and imaging and so on, but the primary thing for measuring the effectiveness of the mission was to see how does the orbit change. And the way that you measure the orbit of a binary asteroid system is via photometry, by measuring a light curve. In a sort of similar way to people look for exoplanets via light curves. Yeah? You're never going to resolve this binary system. It's far too close. These things are too tiny. And so even with the largest telescopes, we're not resolving the binary and we're not getting the orbit directly from the imaging. What we're measuring is the brightness from the light curve. And as this thing orbits, every so often, it's going to cast a shadow on the surface like this. And then when there's a shadow, there's a dip in the brightness. Yeah. Or it's going to have the secondary pass behind the primary like that. And then there's another dip. Yeah. So all you're doing is measuring the total brightness of the system. And from that, you're seeing these regular dips, and that lets you infer what's the orbital period of the moon going around it. Yeah. And so this is what we did. We measure the brightness of the system, and then we can compare when do we see the dips with when would you have seen the dips if it had kept the same orbital period that it had before we hit it. And we were thinking this might take weeks or months to get this answer, but actually we were already picking up these dips and this sensitivity in the days immediately afterwards. And already you could see a drift in when you were seeing the dips compared with where you would expect to see them. And what we found from this orbit change is that we changed this thing by almost half an hour. It's this, the previous orbit was almost 12 hours, 11 hours, 55 minutes. The new orbit, it's going around at 11 hours, 22 minutes. So about half an hour change in the orbit period. The minimum requirement for we should succeed in this was about 6 minutes change. So actually knocked it out of the park, which is good. And that immediately gives us a clue that this beta factor must actually be quite high. It was quite an effective experiment. We also saw this kind of cool explosion. This is images taken of the moment of impact, and you see this bright flash and this stuff coming off of it. This was very unexpected. People weren't expecting to see this thing, and we're only just sort of figuring that out now. And there's a paper that's working its way through the process at the moment, should come out in the next few weeks, explaining what we actually saw here in this impact flash. We had images all over the world. These are just to show that we could, images from every continent, including observations from Antarctica. Didn't get a lot from there because it wasn't a kind of high MS and it was middle of the summer down there, so it wasn't really dark. But we were getting these observations from everywhere. And this is from space, from some nice Hubble and some JWST images. And what you're seeing here is you're seeing a cloud of ejecta coming off. So you've got diffraction spikes, you've got the characteristic JWST pattern. But on top of that, you're seeing this kind of broad fan of material coming out one side. And this is because we've hit this thing and caused a crater, and there's now a bunch of rocks flying off into space and forming this kind of cone shape, and you see this cone from the side. So you see this sort of triangle moving out. The Hubble images are quite nice because you sort of see a sequence of this evolving over hours in the time after the impact. You sort of see this cloud go from quite compact to moving outwards. And then in the days and weeks afterwards, it starts to look like a comet with a tail, because this material that's been thrown off is then swept back into the tail by solar radiation pressure in the same way that comet dust tail is formed. So we started to see the material spread out, but then you have these odd patterns in the hair. And then again, things that we can model and try and understand the actual physics of the process and where did it hit and which direction did the material go. This is a sequence of images taken from ESO VLT. This is work that's led by one of my colleagues in Edinburgh, Cyril Optom, where you're seeing the evolution of this pattern of ejecta over the hours and nights that followed the impact. And yeah, there's a lot of beautiful detail in here. There's also a lot of work looking at the spectroscopy and the composition and how that was changing. And then this is a nice sequence of images that were taken a couple of months later, when it's still, this tail persisted for a long time. We could follow that, we could see that this thing had a comet-like tail of some of the larger debris left around it for months, basically until it wasn't observable again that season. And then also in some of the Hubble images, and it's probably difficult to see on the screens here, but actually you could track individual sort of boulders, so things that would have been the size of these couple of boulders that where it hit. It obviously threw off a lot of these things off into the space, and you could then track them as they moved away and are now going off on their own little orbits around the sun and slowly departing. There's also one of the images, the one that's on the lower left there. This was taken from Lichia cube. This is the much smaller scale. This is this debris from the little CubeSat flying through the debris field. What you're seeing there is the brighter blob is the larger asteroid itself, Didymos, and then the little splat above it is the material leaving from Dimorphos. When the spacecraft team first saw that image, they thought, "Oh God, we've gone too hard. We've destroyed it. It's gone. It was completely splat." But the ground-based observers knew it was still there because we were seeing the dips. So, but yeah, we hit it quite hard and it made a mess. Okay, so the last thing that I wanted to tell you about, though, was about the actual observing the moment of impact and how you actually, because I said we saw this unexpected sort of like flash and fast-moving cloud that moved out, that were coming out from the thing in seconds after the impact. And so to do this, we wanted to have telescope there so we would see the moment of impact. And while we were mostly focusing on the big telescopes at professional observatories and where would we get these good quality light curves to measure the change in the orbit, also we wanted to see this thing just in case, a bright flash thing falls apart. Let's see what happens. But to observe it at an impact time, at the moment of impact, Didymos was sort of overhead the Indian Ocean. And it was about 1 o'clock in the morning here in the UK. So it was dark over Africa and over Europe. It was daylight in the Americas and just sunset in Chile where the telescopes are there. And if you wanted to observe this thing at, less than a couple of air masses, you wanted to be somewhere in the Indian Ocean or southern Africa or southern eastern Africa. The telescopes at the observatory at Sutherland in South Africa were following this thing. But that's about the only professional observatory in that circle. And so we decided that we probably should have at least one more place watching from this. And this happened to overlap with an interest that some of us had in Edinburgh about setting up an observatory in Kenya. There's been people at the ATC, and Martin Wells was one of the people who was really pushing on this for a long time, who see that there's a great potential for an observatory in Kenya. Kenya is right on the equator, so you can see both northern and southern skies. The only place you can't really observe easily is stuff that's right at the poles. So you can see a large fraction of the sky from an observatory there. There's some very, very dark rural areas there. And the northern bits of Kenya are surprisingly arid and dry for somewhere that's on the equator. Most of the equator is just a boiling mess of clouds, and you wouldn't put an observatory there. But there's places in Kenya that have potentially very good sites. And some high mountain stuff there, sort of to 3,000 meter altitude stuff in high and dark places. So potentially very good professional observing sites out there. There's also lots of potential for development there, lots of astrotourism, and nearly everybody that goes to Kenya for tourism goes there with a giant camera to go and take pictures of leopards. Yeah? And then at night just sits there and sleeps and doesn't look at the fact that above them is the best sky they've ever seen because it's so dark out in these game camps. So encouraging a bit of astronomy, having people there that know a bit of astronomy and can teach this and can show that, there's lots of room for development. So there's this organization called Kenya Optical Telescope Initiative. We've been pushing this for years. They happen to have some people here. By chance coincidence, chatting over a mulled wine and mince pie the Christmas before the DART mission about, oh, what are you doing this year? Oh, I've got to go and try and find somewhere in Africa to observe a spacecraft crashing into an asteroid. Funny you should say that. I know a site. We ended up in this place in northern Kenya called the Turkana Basin Institute. Now, Turkana Basin Institute is this research facility on the shores of Lake Turkana in the northern bit of Kenya, almost in Ethiopia. This is a research institute which is mostly kind of funded by private donations and some university funding and associated with some US universities. But it is the VLT of anthropology. This is the place in the world to go and study the early evolution of humanity. Basically, we all came from the Turkana Basin few tens of thousands of years ago. And there are places, you go out there, you wander around, and you're just walking along, you go, oh, look, a little fossil. Oh, yeah, there you go. It's a 2 million-year-old human. There you go. There's nature paper. It's an amazing site out there, and it's a really important area for research into this area. So there's this research institute there, which is in the absolute middle of nowhere, but it has, facilities. It has power, and it has internet, and it has food, and water, and it has labs that are doing very technical, precise work on looking after these priceless fossils. And so you've got everything you'd need to help you set up an observatory. So this is where we thought we'd send a telescope. So we took a telescope out there. We bought ourselves a 40 centimeter Skywatcher Dobsonian on the basis this was the most reasonable big bit of glass we could get for our money and fit in a box and fit in a little plane and take to Kenya. This is us testing it up the hill here, and the fun and games of watching a few professional astronomers try and figure out how to use a small telescope. You would have laughed. You would have loved it. It was really funny. Anyway, we eventually figured out how to use a small telescope where you don't just type on a computer and it works. This is the little plane you have to take to get to this place in the middle of nowhere. This is us landing on this dirt strip out there. The picture there, the first picture is us in Nairobi taking out the back row of seats from this little plane so we can fit our Dobsonian into it to take with us. And this is our observatory. It's the little building that they did have some solar panels on the roof of that they kindly moved out of the way and put on the towers next to the thing instead. And this is us with our little telescope in the middle of nowhere. It's an amazing place to observe, mostly because it's 36 degrees in the shade in the daytime and it's a pleasant 28 for nighttime observing. So shorts and t-shirt, none of this freezing cold Edinburgh dark skies, incredibly dark skies. This is us showing some of the local school kids, like, come and look through a telescope, come and see Saturn for the first time. You've all seen the reaction of people doing this, but yeah, it's amazing. This is one of the Kenyan master students who's now actually studying with us here and doing a PhD, who was helping out with the observing. And this is what we were seeing. Okay, it's not quite the same as some of the nice other data that we had from the 1 meter in Sutherland, but if you watch this thing, this is at the moment of impact, you'll see, boom, yeah. Now, the guys in Kenya knew that the mission worked because they saw that before they saw the feed come in because they had one laptop next to them watching the YouTube of the NASA feed of the spacecraft coming in, and one watching the images come off the telescope. And it went boom, must have hit it. And they went, oh yeah, hit. Which tells you something more about the internet speed out there than the fact that it was going. But actually, you're seeing the light come straight from the impact. You're not seeing the signal get transmitted to NASA, reconstructed into an image, streamed onto YouTube, sent around the world, sent back to you. It's not just the slow speed of internet in rural Africa that was doing that. It was like you do see it more quickly if you're looking directly at the eyepiece and seeing that got brighter. And it did. It got substantially brighter. So this is a light curve from it, and you suddenly see this big spike, and then as the material moves out of the aperture, it starts fading again, and then stays at a higher level, which is this coma that then becomes this tail over the next weeks and months. And from this, and so this data that we got from this little 40-centimeter telescope in the middle of Africa, it was really quite useful at pinning down sort of like the rate at which it brightened. As I said, it's taken a little while to figure out exactly what was going on there. We expected it to look a bit like a comet over weeks. We expected some debris to move out. Nobody expected this flash and this material moving out at kilometers a second. For you to see it in seconds, this thing is still far enough away that the scale that's moving at, it's going really fast. In the end, what that turns out to be is that's actually vaporized rock. What you're seeing is glowing there is emission from sodium and from potassium, and you're seeing ions glowing. And that's why you see this in these images. It's actually glowing vapor from the rock that very quickly moves out and then fades. And yeah, the measurements we got from there and from the telescopes in South Africa were what we needed to figure all this stuff out, because we weren't watching it with any of the other bigger telescopes. The nice thing about this is it's also, as well as the whole, we're going to go and save the world thing, there's a more direct, immediate impact on this, which is this telescope that we used for a few months around the impact. We're still site testing out there. There's a group who are flying out tomorrow, actually, to go out there, and we're going to install weather stations on one of these mountain sites at the other end of the lake. They're a lot more remote. They're potentially a lot better site than where the research station is. But the research station has a little airstrip and has power and water and everything else, and the mountain site is properly remote. But it's potentially a very good site. So there's an expedition going to go and put a weather station up there and do some site testing, and maybe a few years' time we'll have a professional observatory out there. But what the other thing we're doing with this little telescope now is we're using it to train next generation of African astronomers. There's a lot of investment going on in the world of astronomy in the SKA that you've probably heard about, this big new radio telescope. It's going to be the biggest thing. It's this radio telescope that's spread across a vast area of southern Africa and Australia. And so this massive radio array is being built in Africa. And at some point someone asked, are there any radio astronomers in Africa? And there was a sort of embarrassed silence. And I thought, maybe there should be. And so there's this whole thing called DARA, which is Development in Africa with Radio Astronomy, which is training generations of students there in radio astronomy, some of whom will become radio astronomers and actually use the SKA. Many of others are going to go and use those skills in developing economies all over Africa. And so there's this thing which is partially funded by sort of UK development money called DARA, and this is this program teaching astronomy there. And now we're using our little optical telescope to include a bit of actual optical observing as well as the radio stuff on that skill. So that's what's going on out in Kenya right now. In terms of the DART results, there are papers coming out still. As I said, the one on this impact plume will come out in a couple of weeks. A lot of them other major results are out already. There's quite a nice summary paper from Nancy Chabot, who's one of the people who was running this whole show. There's quite a good overview of some of the results if you want to get into the details a bit more. And then the other follow-up is the European Space Agency's mission HERA, which is the next step in this story. So we always joke that there was 2 spacecraft involved in this overall campaign. The Americans they shot it and see what happens, and the European approach is to send a much more complicated thing covered in instruments, and it's going to go and measure all of the effects and so on. And this is HERA. HERA is a proper scientific mission that's going to go into orbit and measure all the effects and look at what the crater looks like and do all of these measurements. The joke is slightly on the Americans. I'll shoot it and see what happens. The joke is also on the Europeans. We were meant to be there first. It was not, because it's European, so it's late. But it is now in space, so it's on its way. The idea is you have these 2 spacecraft. You have one that does the collision and does the shifting. The other one tells you all about it. And we've figured out an awful lot of the physics and a lot what's going on with a dark collision. But some of the things we still want to know, we've not got a measurement of the mass of Dimorphos. And to do that, you want to put spacecraft in orbit around it and measure the mass directly. You want to also have an actual look at this crater and look at what does it look like, what did we really do. So HERA is meant to go and do the sort of crash scene investigation. And this is the idea, yeah, DART goes and does its impact thing, telescopes on Earth tell you what's happened, and then a bit later, HERA, with its own accompanying CubeSats, goes and tests a lot of technology and gets lots of measurements. HERA is on its way. It launched in October from the Cape, just before a hurricane came across the Cape. That was, you can see the sort of darkening skies behind it. It launched in about the only 10-minute window where the sky was remotely clear and was out there. It was ridiculous. When you got there in the morning, you could not see from where you stand to watch the rocket. But somehow it miraculously cleared long enough to get it into space, and then we all ran away before the hurricane arrived. This is another image of it before it launched, obviously, with some people, just again for scale. It's not a very large spacecraft, but it's packed full of scientific instruments. It's got cameras and spectrographs. It's got the first time we'll fly a ground-penetrating radar to an asteroid. So we'll get an idea of what the interior structure of one of these things looks like for the first time. So that's a really exciting thing. That is on its way. It will get there late 2026. It flies past Mars in a couple of months' time. So it should have some nice images coming from that, just on its way. And yeah, that's the next step in the story. We will see what the outcome of the DART mission looks like from in situ in a couple of years' time. I'll stop there and then take any questions.
Thanks very much, Colin. We have a couple of roving mics, if we can get a few hands for questions.
Hi, thanks for the talk. You said you could use the value of beta to scale the impactor, but isn't beta determined by the composition of what it's going to hit? And do you know that ahead of time, or do you only know that after you've hit it?
Yeah, so it will depend on many factors. And in an ideal world, you would do this experiment many times with lots of different asteroids of different types and get an idea of what that would be. If we were ever to do this for real, if we were ever to find an asteroid that's coming towards us, the chances are you find the thing with decades of warning time. And that's probably enough time to send a first kind of reconnaissance mission to go and look at it, spectroscopy, measure its mass, know everything you can know about it, and then figure out, okay, how hard do I have to hit this thing? And so that's the thinking that you would probably have a lot more information if you were doing this for real. If you were doing this for real and you saw something coming with not that much warning, you would just hit it as hard as you possibly could anyway. But yeah, there's lots of interesting. This is why, as I said, these meetings where we talk about planetary defense, there's a lot of politics and there's a lot of interesting stuff that goes on, as well as the astronomy and as well as the rocket science, because as soon as you can move an asteroid to stop it hitting a city, it means you've also got the technology to move an asteroid to make it hit a city. And so you have got a rather potent weapon, and therefore being able to, where you aim it, which way do you nudge it, If this thing's coming towards you and it's going to hit, it's going to hit London, do you nudge it towards France? Do you nudge it towards Dublin? Someone's going to be annoyed if you nudge it the wrong way and don't nudge it enough. So, so there's a lot of other fun discussions that go into it if you were ever doing this for real. But yeah, the beta factor probably depends on many things as well.
Thanks for a great talk. I was wondering about the sort of balance between physics and astronomy, because the physics would say you hit two things, you know what happens. Yeah. Where does the astronomy? Sorry, I'm skeptical, as you can hear.
So the thing is that, like the physics problem, if you're doing this with billiards, this is a solid ball and this is a solid ball, you know exactly what's going to happen. The problem is this thing is a rubble pile that's made up of lots of individual solid balls that are all going to move relative to each other. And it's how do they, of an unknown size distribution, of an unknown material strength, of an unknown shape and configuration. And so the physics, if you knew exactly where all of the mass was and in what type of material, you could solve the problem entirely mathematically. But because this is a large enough system that it's complex enough, You can't do that. There were lots of complex simulations, and there are lots of complex simulations trying to understand exactly how it's worked after the fact. But it's a very, it's not an entirely solvable problem because we don't know all of the original inputs of where all the individual bits are. Although we understand the physics of it, we don't understand all of the original setup of it. Yeah, and that's where doing an experiment like this at scale comes in, because you can do an experiment in a lab where you take a rock this size and you shoot it with a rifle or something, and that's kind of scales. But at some point, gravity is dominated in holding this thing together. And you can't really do that in a lab because you can't make something that's held by gravity instead of material strength and scale it. You have to do the experiment at scale to be doing it with the same physics.
Over here.
Yeah, so following on from that, you didn't really explain, when you see the sort of boulder cloud coming out of it, is there a proportion of boulders that came off the far side from the impact? So was it like a Newton's cradle, where you bang
It's one of the things that
and some of them bounce out?
Yeah, we don't really know exactly where they've all come from. You can't quite trace them all the way back to like this point on the surface because the scales are so different. And that's one of the things that HERA will tell us. We'll see, is all the damage on the side that we hit and the other side looks sort of similar, or is the whole thing being completely rearranged? Do you see an absence of large boulders on the other side because they've come off the other side, right. Or were these things coming out from the interior because you've excavated a really big hole? And so that's one of the things that we should get some clues from when we get images up close of the aftermath.
Okay. I have a question before we go. Back to the beginning of your presentation about scanning and looking for these things coming. What happens will we spot something big coming off the plane, coming from interstellar space, perpendicular to the solar system?
So this is all talking about like near-Earth asteroids, things that are bound orbits in space around Earth and are on orbits that are not overly elongated and so on. That's different from if we're talking about either a long period comet coming out of the Oort cloud or something from interstellar space that comes in that those you don't know before they arrive and then you don't see again after they've gone. These are things that are on orbits that are bound. So those are a different kind of threat, if you want, in that you wouldn't see them coming with a very long time. The other thing that I work on is Comet Interceptor mission. This is to go and look at a long period comet coming in from the Oort cloud. And it has exactly that problem that we don't know the target, and we might not know the target when we launch it. But they're not such a concern from the planetary protection point of view, because space is really big and the Earth's quite a small target for these things that come through quite rarely. Right. And so the odds of impact from something like that are, low. It would be bad if it did, because they're going really fast and they're quite big. But the odds are quite low. If you look at what the sort of integrated impact hazard is, most of it is from asteroids. It's from stuff in the asteroid belt that's migrated into sort of Earth-crossing orbits, and then eventually is in the same place as Earth is at the same time. So those are where we have, the ones that we could potentially do something about are also probably the ones that we should worry about more than the really big ones that we couldn't do much about anyway, and we'd have to be really unlucky.
Right. One more question? Sorry.
Hi, the schoolboy in me wants to know, are you wearing a planetary defense badge? That must be the coolest badge in the world.
There's it's got, like, occasionally you go to these conferences, the planetary defense conference, and then you get a T-shirt from it, and then you're so tempted to like run through the airport on the way back, going out of my way, planetary defense. But yeah.
What?
This isn't really an astronomy question, but the northwest, north of Eldoret and where you are in Turkana is very unstable in Kenya. What are you doing to protect your staff against Al-Shabaab?
That area is actually not too bad. The area in northern Kenya that's a problem is the northeastern bordering onto Somalia and over in that area, and that's somewhere where we wouldn't be going and sending Edinburgh University people or kit out to. But the area in the Turkana Basin, you're far enough away from the border. There's not really any trouble there from that. There's some. We fly because some of the road south between there to Nairobi is a little interesting, but the actual area there is fine. There's no real political issues there. And the nice thing about this research institute is taken a very, a very proactive attitude towards employing everyone locally and bringing them along with, this is why we're doing this research and this interesting thing. And so they're very welcome and very kind of part of the community there. And so, yeah, no, there's no real concerns from the political climate there. That bit is pretty good.
Very good. Can I just ask on Zoom first? Do we have any questions on Zoom? No questions. Okay. On YouTube?
No questions on YouTube.
We have one more here. If I could switch that on, please.
Did they find out anything new or surprising about the composition?
So the composition of it is more or less what we expected from we didn't see a great difference in we had spectroscopy of the asteroid before, and then you had spectroscopy of this cloud of debris of stuff that's probably from the interior, and it looks more or less similar to the surface. So one of the questions was going to be, does the inside look different from the outside? And not really is the answer to that one. It seemed to be largely as expected, that the spectroscopy looks more or less similar. So it supports this idea that this thing's made of a whole bunch of rubble that's come off of the main one and then reaccumulated.
Okay, thank you. Thank you very much. Can we appreciate you? Thank you. We're going over to Nigel now for the sky in January, is it? January.
Okay, so the sky in January, I thought I'd start with a really nice image from Pat Devine of the classic object of deep sky object for this time of year, the M42, the Orion Nebula, which really just sums up this time in the year. So let's look at the sky in January in 2025. First thing to say is we're past the winter solstice, so the nights are getting shorter, but we've still got plenty of darkness around, and that can be seen by the fact that even though we have a situation where the sunset is getting later each evening as the month goes through, even though that's happening, and the astronomical twilight in the evening is also getting later. So the beginning of astronomical dark is getting later. But even so, and the astronomical twilight in the morning is in fact getting earlier. Even with that, we're still getting something like 11 hours and a bit of true darkness when the sky is clear. And just an interesting fact is that on the 3rd of January, Earth was at perihelion, so it was at, despite the fact that we have these long dark nights, the Earth itself is actually closer to the sun than it is in the summertime. Not by a huge amount, but it is closer. And because of the tilt of the Earth, of course, that's why we get our longer, darker nights, rather than how close or far away the Earth is from the sun. So, midwinter skies, let's look at some highlights for the month. Mars, it's really a story of the planets at the moment. Mars, Jupiter and Venus are all well placed, and we've seen that with a number of images from members in the last week or so when we've had some clear nights. There are many conjunctions and occultations with the moon. through the month that make for some interesting observing. And we've just had the peak of the Quadrantids meteor shower, which is a very short meteor shower, which we'll talk about in a moment. We're also going to have a look at once I've gone through the night sky as it's looking for January, we'll look at a particular constellation in a bit more detail. So first of all, looking south here, we can see that the Milky Way is arcing overhead, and it's perhaps on moonless nights it's would be quite a good show, as it's running more or less from south to north, slightly offset. So all of the circumpolar constellations are well represented, and of course at this time of year we have Orion, Gemini and Taurus dominating the view to the south. So going around to the west, the summer and late summer and autumn constellations are now disappearing westward quite quickly, like Cygnus and Andromeda. But Andromeda and Triangulum and these M31, M33 are still relatively high in the sky and still make good targets. Whereas Pegasus itself and Andromeda are, as I say, beginning to disappear from sight. But when we go around to the north, we can see that the Plough is at that stage in its journey around the north celestial pole, where it's kind of standing on its handle, and that's high in the northeast. You've got the constellation of Draco as well, is easily obtainable, as is Cepheus. And then finally, coming around to the east, we're getting the promise of the season for looking at galaxy season, because Leo is becoming more prominent in the east as the nights wear on, as is Canis Venatici and these other constellations that are full of full of galaxies. So let's look at the constellation in a bit more detail, the constellation of Taurus. Taurus is the sixth largest of the zodiacal constellations, and it's the 17th largest constellation of all. It's quite easy to spot because of several objects contained within its borders. It occupies around 797 square degrees of the sky, and it's well known for its star clusters and nebulae. So there's a lot in there to take a look at. We've got star clusters like the Hyades and the Pleiades, and as well as those, we also have a number of other deep sky objects contained within Taurus, which is just up to the north and east of Orion. Taurus has a number of deep sky objects. M1, the Crab Nebula, which is a remnant of a supernova, which exploded in the 11th century, and it's quite well documented, especially by Chinese astronomers of the time. I think it was 1058 that it's been located at. We also have Simius 147, the Spaghetti Nebula, Hines Variable Nebula, and also colliding galaxies NGC 1410 and 1409, the Crystal Ball Nebula, and the Merope Nebula. I hope I'm saying these right. So let's have a look at some of the images that have been coming from members. And first of all, we have the Crab Nebula. This is an image taken by our telescope in Spain and processed by Mike of the Crab Nebula that we were talking about, 1054 CE, my notes say. It's about 6,500 light years from Earth. And although quite a small target, it's a very detailed target. We also have M45, the Pleiades, which are located sort of bright young stars, which is why they're a blue colour, and they're located about 440 light years from Earth, made up of around 1,000 stars. In actual fact, 7 or 8 of which can be seen with the naked eye. They're hot young stars, and the sort of nebulosity around them is actually, in actual fact, the Merope Nebula, in which they are currently embedded, which is where which is a cloud of gas and dust, and it's a reflection nebula because it's reflecting the light from these hot young stars. The Crystal Ball Nebula. This is an excellent image from David Brett. Is also in Taurus, and it's a typical planetary nebula, again near the border with Perseus. Apparent magnitude of 9.43 and a distance of about 2,200 light years from Earth. It has an angular area of 2.2 arc minutes. The Hyades, a wide field image from Fran of the Hyades, including the Pleiades and in fact Jupiter in this particular image. But the Pleiades itself, obviously the main star of Taurus, Aldebaran, and it's an interesting hunting ground for observers and imagers alike. So that's the Hyades there. I couldn't find any images by members of this particular nebula, the Spaghetti Nebula. I may be wrong, but I couldn't find them online. So please let me know if somebody has actually imaged that. It's something I'd be quite interested in. It's quite a large, several times the diameter of the full moon, so it's quite a large, but I presume quite a faint nebula. And again, it's between the horns of Taurus. Heinz Variable Nebula. This was a nebula which was discovered by Mr. Heinz in 1858, I think, and it's the only nebula that we know of that varies in brightness over time. I don't think we know why that happens, but it does. It's hence the name, the Variable Nebula. Okay, so Taurus, an interesting and a very well-placed constellation for imagers and observers alike at the moment through January. The moon itself, an excellent background image by John here of Plato and the northern part of the moon. The moon phases for January. The first quarter has just gone. The full moon is on the 13th, and the third quarter phase is on the 21st of January, with new moon on the 29th. So really the second half of January, for those people who are not particularly wanting to image the moon, but would like to go after deep sky, then it's the second half of the month that we need to be looking at. The moon, as I mentioned at the beginning of the talk, there's a number of close approaches to various other objects in the night sky. There's a close approach of the Moon and Venus on the 3rd of January that's just gone past. There was the lunar occultation of Saturn on the 4th, and we'll look at some images that members took on that. The Moon will occult Neptune on the 5th of January, has occulted Neptune on the 5th of January, and it's at perigee in relation to the Earth on the 8th of January, and apogee furthest away from the Earth on the 21st. There's a close approach of the Moon with M45 and Jupiter on this evening, tonight, which would make an interesting wide field image, I think. So here are some images that were taken. We had an online event that Mark organised, and here is just some images that I managed to pick off the website. David's image here, a sort of daylight image, I think with his phone. You can see that Saturn is just approaching the dark limb of the Moon, and another one by Mark Sansom with, you can just about see a little bright speck in there of Saturn, and approaching the dark limb of the Moon, and also another image where it has gone behind the Moon and has reappeared on the light limb of the Moon. Now, I mentioned the planets. Planets, again, particularly Venus, Mars and Jupiter, are all well placed this month. So let's first of all take a look at Jupiter. This is a nice image by David Brett. Jupiter is very easy to find, not just because it's bright, but because of its proximity at the moment to the Hyades and the Pleiades. Mars, again, is a very, it's approaching opposition. It will reach opposition pretty soon, and it rises in the northeast, reaches the highest point in the night sky around about midnight, 59 degrees, so it's good and high. So you should be able to get less interference from the atmosphere. And this is an excellent image by Ron Morley. Opposition on the 16th of January. Saturn, Venus, Uranus and Neptune are in the area of Pisces and Aquarius, so they're towards the west, and they're quite low down. Saturn is on its way to disappearing for the rest of the year. Venus is a bright object in the early evening at the moment, as you know. There's a close approach of Venus and Saturn on the 18th, and conjunction on the 20th of January. So again, that would be an interesting view for observers and for imagers. Let's take a quick look at comets. Of the comets that I was researching that are visible from Edinburgh at this time of year, and the ones that are actually brightening, only two really are feasible. Sushinshan, comet 60P, visible around 5:45 in the evening, 43 degrees above the southern horizon in Pisces, as it begins to turn dark. It'll then sink towards the horizon, setting at midnight. And this is the track of 60P going from the 9th of January on the right-hand side there to the end of the month and into February on the left-hand side. And the other comet, which is visible and is actually brightening at the moment, is comet 43P Wolf-Harrington, visible in Aries. becomes accessible to us around about 5:45 again, above the southeast horizon, reaching the highest point in the sky at about 6:45, 48 degrees above the southern horizon. And it will continue to be observable to round about 11:30, after which it sinks towards the west. And this is the track for the 43P Wolf-Harrington, again going from left to right through the month of January. And I mentioned the quadrantid meteor shower, which has just taken place. It's named after a now defunct constellation, the Quadrant, which was didn't make the cut when the Astronomical Union decided to settle on the 88 constellations of the night sky. But it's still called the quadrantid meteor shower. And it has it's circumpolar. It has a very short life, so but it can produce up to 100 meteors per hour, and some quite bright ones as well. And I think that actually covers everything I wanted to talk about. So thank you very much, and clear skies.
Thank you very much, and thank you for fighting the technology. Well, that's it for this evening. Tea and coffee are available. And thanks to everybody out there listening online.